Lecture, we'll be looking at fatigue analysis under moving loads. So under this particular lecture, we'll be looking specifically at steel bridges, what happens in terms of fatigue, how do you assess the fatigue strength, what are the available methods that are there, how do you distinguish fatigue, the fatigue strength of a material. We'll look at small examples in terms of a gantry girder, in terms of understanding how do you assess the fatigue strength in case of a simple problem. We'll look at a bridge example wherein the application of whatever we are going to say, the methods that are available will be discussed, right? Why are we looking at steel bridges is because of the problem that the fatigue kind of governs the design in case of steel structures more, steel bridges more, because the weight of the concrete bridge, when you use a higher strength material that you have in terms of steel structures, the section sizes or the dimensions or the weight of the bridge in itself becomes a lighter weight. So the self weight is there, but when you move a rolling load, which Vice sir was explaining, first of all, damping is less in terms of steel structures. Then again, when the live load fluctuation happens, the stress range increases. So in terms of fatigue load, in terms of design of bridges under fatigue, strength and serviceability takes a backseat, and most of the times the fatigue is what governs the design. And in that design, the stress range, that is a difference between the peak stresses, the maximum and the minimum stress, which I call the difference as the stress range, governs the kind of fatigue analysis, right? I hope it is clear. The stress range, the peak difference between the maximum and minimum. Why is it important in steel bridges? I've explained. I hope with this particular thing we'll start our discussion or the lecture. Now whenever I ask anyone what is the fatigue strength of a particular material, what is fatigue analysis, why does it matter to you, we normally tend to move in terms of, okay sir, there is a high cycle fatigue, there is a low cycle fatigue. In high cycle fatigue, the stresses are within the elastic limit. Yes, in fatigue, cyclic loading is there, so some cyclic stresses are being applied. In terms of in terms of low cycle fatigue, we say these stresses, the cyclic loading or the cyclic stresses are still there, but the stress which is applied is beyond its yield limit, so it is going into the plastic deformation limit, etc. But this is the definition of what you call between as a high cycle fatigue and a low cycle fatigue. But fatigue as it is, the definition you need to understand is that fatigue is the initiation and propagation of micro cracks into macro cracks by the repeated application of stresses. So you have a certain crack, either it is not present or it becomes present due to the stress concentration of a flaw in a material, and that crack initiates and propagates into a macro crack due to the application of cyclic loads or stresses. That is known as fatigue. Later, when we talk about, okay, high cycle or low cycle, there is a definition that comes in where the stresses we quantify as being in the elastic limit or being in the non-linear range. Understand? So fatigue failure occurs mainly as a mechanical fatigue. What are the different classification of fatigue? Is mechanical, where the loads are applied in a cyclic manner. Creep is where the cyclic loads are still there, but we are looking at the fatigue at a very high temperature. Thermomechanical is where the temperature as well as the loading is in a cyclic manner. And corrosion fatigue is when the material is corroded, and we are looking at the fatigue strength of that particular thing. So corrosion and fatigue both acts in terms of we are looking at the corrosion fatigue kind of a thing. And fatigue, we don't talk about fatigue in terms of buildings as such, because the stress range or the stress fluctuation doesn't happen more. But it may be important in terms of where the machines or moving machines or vibrating machines are kept. Their fatigue might have to be understood in terms of whether it becomes critical or not. But irrespective of that, structures like bridges, gantry girders, cranes, open tower structures like what do you say, power line, that structure that you have, which is subjected to wind loads, those are all subjected to cyclic loads, like offshore platforms, wherein the wave loading comes in as the mechanism which cyclic loading is applied onto it, right? In bridges, it is the moving loads, the vehicle that is moving on top of it. In open tower structures, a power line kind of a structure, the steel structure that stands, wind governs there. In offshore platform, the wave is what applies the cyclic loading. Now, again, as per the fatigue definition that we have explained in the first line of this particular slide, the fatigue failure involves 4 typical stages. Like, one is a crack initiation at point of concentrated stresses. So the fatigue, as in it evolves by the beginning with the crack initiation at point of concentrated stresses. Then the crack grows, then the crack propagates. I mean, there will be it will propagate in the material itself with the final fracture that is happening in the material that ends the fatigue kind of a phenomena if it happens. So cyclic load can cause crack initiation, the crack grows, propagates, and then final rupture happens. And the crack initiation always occurs at the point of flaw in the material location of stress concentration. So if your detail or the bridge design or any structural design has certain areas where stress concentration can occur, or if there is a flaw can occur due to welding, like if I weld there might be some pores which are left inside the weld, those acts as the point from where the crack can initiate in terms of, let's say, weld, that flaw that I mentioned right now, there is a crack in the weld at the root. Even in that case, there is no initiation phase of crack, the crack is already there when the welding has happened. Or in stress concentration location, there is no crack, but due to the stress getting concentrated at those locations, the crack may initiate at that location, causing the phenomena, the fatigue phenomena, to kind of initiate. Yes, in both cases, what we have discussed, whether it is flaw or stress concentration, we are talking about two things happening. Cyclic loading is there. I mean, there is a stress range that is getting developed as the vehicle is moving or the wave is attacking the particular structure. There is fluctuation in the stresses, which we define as the stress range as the important parameter there. And then there are these kind of localized areas where this particular stress concentration or the kind of slip or yielding occurs, right? We'll come to why I said yielding in just a bit. Now, what I all urge every member who is there, I mean, attending this lecture, to look at this particular video that is available in YouTube with respect to experiments with bubble model of metal structures. So what they have done is, yes, we know steel has a crystalline structure wherein you have at the atoms or molecules levels the crystals arranged in certain arrangement. What they have done is they have made in terms of a soap bubbles they have created on a film of soap. And what they have done, I mean, through air bubble, I mean, the air bubbles have been created on a soap film, and they are trying to say that, okay, this has the same representation as in a case of a crystal lattice, where the steel is an alloy, you have different atoms being arranged and kept on top of one another. And what this soap bubble, I mean, you can see at a very close range that these are soap bubbles arranged, and there are certain grain boundaries to this. So this is exactly the way a structural steel looks like.
Hello, Ashwin sir. All the participants are requested to just wait for 2 minutes. The teacher is going to rejoin.
Sorry, Aman, there was a power outage, so I couldn't join. Aman, can you hear me now?
Right. Yes, sir, I can hear you.
Sorry for the slight
No
disturbance that
problem.
we.
No.
So, is my presentation visible?
Yes, it is
Yeah,
visible.
yeah. So we were talking about a model that they had made, wherein we can see the crystal boundaries where these are there, and we'll see now a short video of it. So if you can easily see the video, you can see that when he is compressing the soap bubbles from left to right, you can see certain striations marked, certain things moving from left to right at the grain boundaries. So there is some slip that is happening between the grains, like in between the atoms or molecules, there is slippage. So you can see if I deform the material, there are certain permanent dislocations that are happening. There will be like if the deformations are small, that it may be kind of elastically coming back to rest. So why I showed this video, I recommend everyone. I mean, this is just a small bit of the 16-minute video that is there with respect to experiment with bubble models. There you can easily understand what means like a dislocation, what happens when a metal plastically deforms. There is a certain permanent set that is developed in a metal. If you do an elastic analysis, or if you have voids that are there in terms of a crystalline structure, what does it tend to do? Everything is provided here. Why I said, I mean, shown this particular video has a certain meaning here, and I'll come to that, and I'll tell you what is most important there. So coming back to our discussion about fatigue, the progressive cracking with respect to when a fatigue load is applied on a metal or a steel, structural steel, the cracking usually results in striation marks, which are concentric rings that point towards the area of initiation. So you can see a cross section of, let's say, a coupon that is there, which has been subjected to cyclic loading. So you can see that whatever, whenever we learn structural steel, our teachers tell us like the steel will be a ductile material. So when I say a ductile material, when I look at the fractured surface of that particular material after it has been tested under monotonic test, we intend to see, I mean, we intend to hear that our teachers say there will be a dimple mark, which signifies the ductile failure. But in terms of fatigue failure, the fractured surface will look exactly like this. So you have certain beach marks, like you can see certain locations which point to the origin of the fracture. Here is where the fracture originates, and then you have these beach marks or striations that happens like concentric rings, which propagates, which shows the propagation of the failure surface. So you have certain areas where the metal will leave its contact, and there will be certain reduction in the tensile stress area over which the load will act. So after a certain limit, after the crack has initiated and it has propagated, the reduced area of cross section will be what remains and carries the load. So after a certain limit is reached, then sudden brittle failure may occur. So this catastrophic structure, so the kind of सेम इमेज लाइक इलेक्ट्रॉन माइक्रोस्कोप के अंदर आप रख के if you look at the cross sectional image of this thing, you will see a certain area where this kind of a formation will show a brittle failure, but that has originated due to the crack either already present due to the welding problem. Like if I do a welding improperly, the crack which I said initiates, the initiation might not be there, the crack is already there. Or in terms of a smooth surface, the crack initiates as the cyclic loading is applied, and then it propagates, the fatigue crack propagates, and then as the cross sectional area reduces to a certain critical limit, then the complete fracture of the specimen occurs. The next important point that we should understand before we go into this particular lecture is like final failure generally occurs in the region of tensile stresses. You can understand that whether it is low cycle fatigue, whether it is high cycle fatigue, the fracture or the final failure occurs in the region of tensile stresses, right? This has a meaning going forward. So keep in mind that okay, under compression it might buckle. The final fracture, I mean, the buckling can also aid in creating that concentration of stresses in the member, but the final failure generally occurs in the region of tensile stresses. And this is the most important line that I want to tell you. That is why that video had come in, is that fatigue damage of structures subjected to elastic stress fluctuations, which is what we would expect in a high cycle range, and which is what we would expect in a deck of a bridge, like elastic stresses. हम high cycle fatigue region में ही खेलते हैं in terms of when we are looking at a bridge. So in terms of when a fatigue damage of structures subjected to elastic stress fluctuation occurs in region where the localized stresses exceeds the yield stress of material. So you understand that even when I say in a high cycle fatigue where the stress range is within the elastic limit, the location where the stress concentration occurs or a flaw, this thing, that crack initiation jahan pe bhi hoga at that atomic level or molecular level, there will be a slip or there will be a non-linear, that the stresses will increase beyond the yield stress of the material. So that is what causes the initial flaw or the initial slip creation happens due to the localized area where the stresses goes beyond the yield stress of material, right? So that distinction should be understood, that even when the stresses are below elastic stress at that location, things can go beyond that. So what causes these stresses to go beyond that particular, why that stress concentration occurs, is because there might be sudden change of member geometry. A straight member suddenly changing its orientation can cause it. I mean, the stress concentration, that is what I'm explaining. Or you can have a bolt hole. I mean, there is a sudden hole in the whole cross section when it is subjected to a uniaxial tensile stress. I'll show you the image where the stress concentration, you can easily imagine why the stress concentration might occur around the bolt hole or connections. Then manufacturing process, even the kind of flaw or stress concentration can start even at the point where the steel is getting manufactured through inclusions. Like, it's an alloy, right? You're adding many metals inside to create that particular metal, and then it is rolled under a mill scale, so that might provide some kind of problem. And while fabrication is being done, manufacturing process, I said the previous one, the subsequent fabrication, a person who is cutting a steel plate using a flame cutter, it might provide a rough surface which may be again joined with another metal by some welding or not. That also creates a kind of flaw in the structural assembly that you might be creating for your bridge deck, right? And then welded members, I mean, in terms of steel structures, yes, in comparison to bolted connections, the welded connections create a more tendency for getting fractured under fatigue. It is more prone to it. Why? Because most welding process results in discontinuities. Crack initiation period, as I said, may not even exist for such kind of welded structures. Structural welds have very rough profiles. Why? What do I mean? See, I don't want to intend to say that all welded structures are dangerous. I mean, we should not provide welding at all. We should all go for bolting. The intention to say this is, if you improve your process, if you improve your welding process, if you understand the welding process, such kind of flaws can be not totally eliminated, can be reduced to the maximum possibility. You can use some kind of NDT techniques like dye penetration test, ultrasonic test. You can do radiographic, I mean RT test, and all, to identify whether the flaws are there, I mean, in large quantity. Then you have to discard that member totally for your this for your structure. So certain flaws due to in a welded member is what has been shown here. You have a butt welding which is given here, a complete joint penetration U weld, let's say double U kind of a weld, and there is lack of fusion. If it depends upon how fast you are taking, what electrode you are using, what is the condition of the welder, that what current and what voltage is applying to do that welding, which welding process he is doing, MIG welding, stick welding. In that terms, everything comes in. So if there is a toe crack, like this is a fillet weld, you have a weld that is there, and at the toe of the weld, there can be a crack that can propagate or initiate at these locations. So you are heating that particular area, a large kind of, there is a geometry difference that is coming in, which are all ingredients for stress concentration that can occur, right? This is an image of a plate in which a hole is there, and then it is subjected to uniaxial tension. You can see, if I do my calculation for the average stress, things are okay. But if I look at the actual finite element model, I can see that at the location of these, at the edges of the holes, you have an increment in stress that causes a stress concentration. Same as if there is a notch in the plate, if I cut the plate and arrange it in this way, this particular location at the corners, they have an increment in stress. So suddenly what is happening, if I do my fatigue calculation based on the average stress, it will throw a value that things are safe. But if I take my stress range based on the maximum stress and the minimum stress at this particular location, then it may throw off that the material is, or the assembly is not good enough, right? So you need to do a kind of, sometimes you are not able to understand what is the stress range that is coming in the material. You need to do an FEM analysis to understand. So around the hole, you can see the internal force lines are very dense around the bolt hole, which if you can do a finite element analysis, you can see the stress range is very high. I mean, stress concentration is very high. And this is not just the, I mean, a hole or a weld, but it is also in the bolt. like you have threading around the bolt, and there is a dimension change between the head and the shank. So these are all the locations where the stress concentration can occur. So nobody is immune to fatigue damage, but it is about the designer and the fabricator and everyone coming together. If the process is done right, then fatigue damage will not occur. Again, certain flaws that can occur, right? You see they have tried to do a complete joint penetration weld here from left and right. This type of welding is being done, but then certain holes or it is incompletely penetration. So these kind of act as the point where the crack has already initiated. I mean, the crack is already there, or the deformity or the flaw is already there, and then it tends to propagate from there. And then the geometry thing that I explained earlier. See, if you have a geometry, it changes here, you have a point where the stress concentration will occur, and that cannot, no, in this particular example, that has led to the fracture in this particular girder that is there, this bridge girder, right? You can see this has initiated due to a weld. So these are two different images here. The from a weld kind of a deformity, the crack has propagated, and here due to geometry, the crack has propagated, right? Some examples, like in terms of an offshore structure that you see, this is an example of Alexander K-Land rig, where this oil rig is supported on 5 columns or 5 pontoons, columns which are supporting that whole oil rig. The final fracture that happened is due to a small deflection. I mean, they had welded this particular, they had provided some instrumentation here with respect to this particular brace which were holding the columns in a stiff manner. The fracture in this particular brace member led to the collapse of the total column member as it is, and which led to the capsization of this particular oil rig. Again, a viaduct, a Kinzua viaduct, you think of what is the mistake that they made is, was it was made in 1882 to carry a railroad. A railroad bridge was formed. Due to the higher load at a subsequent years, when the loads increased on the bridge, what they did is they demolished the original structure, they rebuilt a new steel structure to carry that increased load. But what the problem was, the bolts from the original bridge were retained. The anchor bolts which were at the bottom, like if you can look at this particular image, the anchor bolt at the bottom was retained. So when in the new bridge in 2003, under wind forces, not even earthquake force, under wind forces, due to the fluctuation of stresses, the anchor bolt between the washer and the bolt area between the bearing, it fractured due to the fatigue action of that particular wind forces. So it failed, and the total collapse of the bridge happened. You can read when we distribute this particular PPT, or you can Google it up, this particular failure, and you can see the same thing. Upon deep inspection of that cross section of that fractured surface, they saw, I mean, if it anything fractures due to some other type of loading, let's say an earthquake or something like that, we can identify and see whether it is due to fatigue or whether it is due to any other kind of brittle manner or not. So if you see beach marks, striations followed by a brittle surface area, it is easy to understand that that has been done due to fatigue, right? Now this is one last example. It is for a silver bridge that is there. It is a suspension bridge, and what happened was that due to erection easiness, what they did is at the eye, like this is the suspender there, and this is the suspension cable that is there. This is the vertical member that got attached to it. To ease the attachment of the vertical member with the suspension cable, they increased this particular area, they increased the size where the pin has to come in. The wedge that is there where the pin comes in, they intentionally increase the spacing between them so that you can easily fix in the pin which is attaching this particular pin. So what happened is that in that gap, corrosion started occurring. So you have tensile stresses and that pin location where the corrosion was happening. So corrosion fatigue phenomena came into picture, which caused the final collapse of the structure, causing loss of death, right? So what do we understand till now? Yes, fatigue phenomena is there. It is like the growth of the micro crack to the macro crack. It happens in certain stages, that is crack initiation, then crack growth, then crack propagation, and finally when the cross section is not enough to hold up that kind of stresses that is being applied, it fractures. So what are the factors affecting fatigue life? Yes, number of cycles. How many number of cycles can the material take up, of the loading it can take up, that affects the kind of fatigue life that the member can have. Then stress concentration. Yes, obviously you know that if the stress concentration is very high at a certain region, the fatigue life will be very low. Residual stresses, as you know, in a steel structure, when it is fabricated or even when it is manufactured in a roll mill, when it's hot rolled, so residual stresses which are set in equilibrium is formed in the steel metal. So you can say residual stresses as a secondary effect in terms of fatigue life, but you understand if there are certain areas where the residual stresses, the tensile residual stresses are very high, and you know that the final fracture occurs in the tension, then you can think of that it reduces the fatigue strength. Whereas if the residual stresses are, I mean, you cannot control that particular kind of this thing. If it is in compressive phase, then those locations the fatigue strength will be high because it has some kind of a protection from the tensile stresses that is happening there. Plate thickness, I mean, you might be of the thinking that okay, irrespective of the what would plate thickness have a role in this thing, you need to understand that as the plate thickness increases, statistically the flaws or the internal pores or anything that the material initial inclusions in a material that is produced or manufactured will increase. So increase in plate thickness can decrease the fatigue life of the member. And similarly, if you see the code, it gives, if your plate thickness is greater than 25 mm, there is a correction factor for the fatigue strength, that mu value is given, a factor mu is given to do this particular kind of plate correction. And also if you're doing welding or for a thick plate, the kind of heat input and the kind of welding that you do creates more locations wherein, or creates more kind of conditions for a thick plate that the fatigue strength is going to reduce. Imperfection, as stress concentration is there, if more imperfections are there, yes, the fatigue strength is going to reduce. Now this is important. I mean, there will be many questions that I'll pose to you after you listen to this lecture, that whatever we are doing in terms of fatigue assessment, will it is it correct, is there anything missing, many things I'll tell you today. So material strength, so right now, you know, the RDSO code allows you to use up to a material strength of, or a structural steel strength of E350 grade. Majority of the older steel bridges or the ones that are being formed are also of E250 grade also. So maximum we can use E350. Now if I ask you, does material strength play a part? Yes, but in our understanding there are equations that are given, like the fatigue limit. I'll tell you what fatigue limit or fatigue strength is there. If there is an increase in the fatigue strength, if the grade of the plate increases, which means all in all indications what I've said right now is, if I increase the grade of steel, there is a good chance that my fatigue strength has also increased, which is good for me. But in later slides I'll show you that there are certain misconception regarding that particular thing also, regarding the whole range of fatigue cycles, at high cycle and low cycle there is a difference there. Then stress ratio, even though I said stress range, that is F max minus F minimum is what I call as the stress range. Stress ratio doesn't play much of a role, even though if I say F max divided by F minimum or F minimum divided by F max doesn't act as a main particular thing, but it is stress range, not stress ratio, which plays a major role. Now these are post weld treatment. I mean, if I do good treatment, I mean, of the weld, if I try to find out if there is any flaw or anything, or if I smoothen the surface after welding, if you see the surface that is there, there is a reinforcement weld that is there. There are instances or ways in which certain post weld treatment or checking or NDT checking can help you identify. So post weld treatment always helps in increasing the fatigue strength of the assembly, right? And service temperature of the steel is also playing. It's like talking about the creep or the thermomechanical fatigue that we are talking about. So if we identify that, it is, if you identify what temperature range is going to work, it is also going to help your fatigue life. And environmental factors is like corrosion. I want to identify corrosion here, that if corrosion happens, obviously there will be a loss of thickness that you already know in the material. But does corrosion affect the yield and ultimate strength and ductility of the steel? Let's look through the slides and let us understand that yes, corrosion does affect the fatigue strength in a negative way. The fatigue strength decreases, but what all things are all we are ignoring? I mean, our understanding with respect to structural steel is there. Let us improve it so that our steel bridges are more robust in terms of tackling the fatigue. Now, in this particular lecture, we'll be looking at only high cycle fatigue in terms of bridges. That is why there is low cycle fatigue, there is extremely low cycle fatigue, and there is ultra low cycle fatigue also that comes into picture. So just to get on with the definition, yes, high cycle fatigue mode is stress control, where we're looking at the load or the stress range for our matter and associated with really low stress levels that are relevant to predominantly elastic components. Yes, our bridge deck are designed to be remaining elastic under moving loads that are there. Even under earthquake, if you see the RDSO code, what is the response reduction factor that you need to take? The R will be nearly 1, or I think 2 is also mentioned there. So we need that particular deck under moving load to remain essentially elastic. And in this particular high cycle fatigue, we say if the number of cycles is greater than 10 power 5. I've marked that 10 power 5 very specifically because it depends. I mean, it is not a specific number. Yes, in our code, 10 power 5 has a certain importance. 2 into 10 power 5, 5 into 10 power 5, that number is there. Some literature says more than 10 power 7 is high cycle fatigue. Some says less than 10 power 4 is low cycle fatigue. So there is a difference. So what you need to understand is all might be saying differently, but a certain number of a million cycle or things like that is where the high cycle fatigue range grows, but it's not a definite number. Specifically, it depends upon whether your steel is a ferrous alloy, or I mean, if you look at aluminium also, it might have a different kind of thing. So don't kind of stereotype that fatigue into, oh no, you said it wrong, you said it is like greater than 10.45. He is also right, the person who is saying 10 power 6 is also right. It depends upon what metal you are looking at in terms of where it is getting applied, right? Then you have low cycle fatigue, where Coffin-Manson relation comes in, where you are looking, plastic deformation is happening. The stresses, cyclic loads are being applied, and the stresses are going beyond the elastic level. That is where we say the low cycle fatigue picture comes into being, right? And then there is extremely low cycle fatigue model, where the under the fatigue load we expect the failure to be less than 100 cycles. So it is not 10 million, less than 10 power 6, greater than 20 power 6. No, it is less than 100 cycles, where the fatigue load, if applied, can cause the failure of the material, right? One such extremely low cycle fatigue is with respect to where we expect during earthquake, where there are steel structures. I mean, whether it is not about bridges that I'm talking about, bridge deck, not I'm talking about, let's say, beam column joint, which is subjected to earthquake. Where earthquake, you understand that we are using response reduction factor, we are using response reduction factor to kind of reduce the earthquake forces that is imparted to the structure, because we want to depend upon the nonlinear deformation or ductility of the metal to kind of dissipate the earthquake energy, right? So in those cases, 30-second earthquake that we yesterday talked about, the cyclic deformation might be, I mean, 20 cycles might be more than enough to fracture that material. So all these concepts, there is a ultra low cycle fatigue which corresponds to earthquake. There is high cycle fatigue which corresponds to bridge deck. All these are under cyclic load itself, but the number of loads are very much in stark difference, because in one case, in the bridge deck, it is subjected, the stresses that are developed are in the elastic range itself. Here it is into totally into nonlinear range itself. So but the commonality between both the fatigue is the definition that we started off with is, there there is a crack initiation stage, there is a crack growth stage, there is a crack propagation, and final fracture. That is common in the fatigue damage that we see across, whether it is ultra low cycle or whether it is high cycle fatigue, right? So this is an image of that ultra low cycle fatigue failure, a coupon specimen being subjected to cyclic load. You can see a certain region where the red color is generating, that is where the stress concentration is happening because of the load that we are applying. The geometry says that it is, the stress concentration is happening at certain region, right? So that is what I want to understand. So this is ultra low cycle fatigue, less than 10 to 20 cycles. Very high cycle fatigue, 10 power 6 to 10 power 7. And then you understand this is certain image taken from a particular textbook, but I didn't give the reference to it, because giving it means I'm authoritating that this is the range 10 power 4, because certain range will give you different values. 10 power 5. I hope you understood what I wanted to say. Now, this image, I mean, you need to look at it thoroughly. What it says is that, okay, if I look at a material which has been fractured under high cycle fatigue, or one which is under ultra low cycle fatigue, what type of a surface damage do I see? What type of fracture surface do I see? What is playing? I mean, in high cycle fatigue, I said stress is what we mentioned. I mean, because it is elastic stress, I mean, we are playing in that particular region. So stress factor, stress is the main thing that we are concerned about. In terms of low cycle fatigue and extremely low cycle fatigue, the deformation into the plastic region is what matters more. So we talk more about deformation and strain and those kind of things, right? So this is just to give you an idea. Now, from here on, what we'll talk about is bridges, where we expect high cycle fatigue to come. fatigue which occurs due to cyclic variation of the loads that is being applied, and the load that is being applied onto a bridge deck can be of bridge deck or any structure. I mean, currently it is neutral. It says it can be of a constant amplitude loading, or it can be of a variable amplitude loading history can be applied, right? A constant amplitude loading you can think of in a kind of structure or a building where a machine is kept which is vibrating at a constant forcing frequency, right? So it's a constant amplitude that you have. This is a constant amplitude loading that can occur. And then in case of bridges or earthquakes, we have a variable amplitude loading history. So keep in mind that under fatigue, yes, the classification is there, but even in terms of loading that is occurring in terms of a fatigue loading, there are two classifications. One is constant amplitude loading, one is variable amplitude loading. Keep this in mind because the SN curve that we are going to discuss with respect to your code is currently based upon the constant amplitude loading that we have, right? So we have to mention that thing. So our aim with respect to the stress method, which signifies the high cycle fatigue, which is expected in a bridge deck, the aim is to find out the fatigue strength under the fluctuating load, right? Due to the moving load, what is the fatigue strength of my assembly or my connection or my member, right? So the fatigue strength, understand this property. There will be many definitions coming now. One is fatigue strength, one is fatigue limit, and one is cutoff limit. These are the three explanation that is going to come in, and all have a certain importance. So fatigue strength is defined as the range of cyclic stress a material can withstand without causing any failure, right? So we are saying there is a range of stress, I mean, that the material can be applied to. How many number of cycles can it undergo? I mean, without causing any failure is what we are talking of in terms of fatigue strength. A fatigue limit or an endurance limit is defined as the maximum value of stress range that can be repeated an infinite number of times without causing any failure, right? So there is a difference. Fatigue strength is like if I have the stress range, how many number of cycles can it take up? So we are talking about a connection or a plate or a weld or any kind of that kind of joint. We are talking about this thing. Fatigue limit is how through testing we can find out a particular stress range. Let's say 50 MPa is the stress range. If I keep my stress range below that particular level, I can have infinite life in the member. That is a fatigue limit, right? So structural components in terms of bridges are designed accordingly that no local yielding occurs to initiate a crack. So if I keep my stresses below the fatigue limit, obviously in that particular assembly or a member, it will not undergo that fatigue failure, right? And there is an infinite life and a limited life concept. The same as what I explained. Infinite life means if I keep my stress range below that fatigue limit, yes, it will have an infinite life. But if I have a certain other way of designing is that I'm not looking at key, I want too much kind of safety in my member. If I look at key, okay, if I know how many cycles are being applied to the member, I know the number of cycles, and I know the stress life, stress range that the member is going to subject it to, I can say, okay, well, see, this is the number of cycles that is expected for this type of material joint or detail category. If this is the stress range I'm applying, the number of cycles that can survive is more than what is being subjected to. So that is limited life concept that is there. I hope you can understand like fatigue limit as well as the limited life concept as two things. So normally an SN curve looks like the stress range is on the y-axis and the cycle for stresses n is like this. So for a ferrous alloy, like our steel structures, there may be a point, a kink, where you can see that infinite life concept ko, if I want to explain like this, I'll say I'll keep my stress range for a ferrous alloy here where my cursor is right now. If I keep my stress range, how can I reduce the stress range in a material? Let's say at the beginning, the stress range in the material was this. Stress range means under moving load, what is the maximum and minimum stresses that are developed? Initially, it is this. If I want to reduce my stress range, what I can do, I can increase the size of my member. Let's say beam or a girder, I can increase. That way, I can reduce the stress range. So if I reduce my stress range, then if I'm looking at, let's say a bridge deck or something like that, I need to bring it this particular level. That means this is the point that I'm saying with respect to fatigue limit. So if I keep my stress range here, that member or the assembly will have infinite life. But if I am looking at a gantry girder, whose problem example that we are doing, We understand that it will be operational for a certain number of times in a particular day, and that will be done over the years, and then the service life of the building might be 50 years. So you expect a certain stress range to be developed there in that particular detail category will come to its own. And then we know how many number of cycles can it survive. So if I look at separately what is the number of cycles that particular crane or a girder will be subjected to, and if I find out what is the fatigue life of that particular thing, if my fatigue life is more than the number of times that loading is going to come, my design is safe. That is the limited life concept that is there, because I'm not interested in having that member an infinite life that is there. So SN curve, you have SN curve represents the relationship between, I mean, we'll go forward with this particular discussion, and I'm sure that you will understand. There are further slides and examples that are there which will improve your understanding regarding this. So we have the SN curve, which represents the relationship between the number of cycles for fracture and the maximum stress or stress range. Just to clarify here itself, stress range, मैं बार बार बोल रहा हूँ, how do you calculate is, in the morning class, sir said, okay, you have different methods of doing the moving load analysis on a, let's say, a simply supported beam that was there. The beam has an I section. Let's assume that it's an I section. The cross section is an I section. You run the moving vehicle on top of it, and you find out what is the maximum, let's say, normal stress or flexural stress that is developed in the flange material, or the shear stress that is developed in the web girder, right? If you find out that particular stress, due to the moving load, the stresses will range from a peak value. If you're looking at a particular cross section, you will say when the vehicle wheel is on top of that particular, single wheel is on top of that particular point, it will give a maximum value. But when it moves on, there will be a minimum value also coming in. So if I find out the difference between the maximum stress and the minimum stress, that gives me the stress range, right? And then I need to understand how many number of cycles will it survive. If I get a value, then I have to check how many number of cycles will come really when the vehicle moves it. So to prepare an SN curve, there are different methods that are available. You have the nominal stress method, structural hotspot stress method, north stress method, and everything. The SN curve that is given in IS 800 2007 or RDSO code is based on the nominal stress method, which is like the this approach is based on the average stress corresponding to a particular cross section. The stress has been calculated using the assumption of linear elastic theory, and M by I, F by Y, those kind of the mechanics of materials जो आप पढ़ के आए हैं, that is being used to calculate that particular stresses, right? And local effect that causes stress magnification is neglected. But yes, if you do a lot of test, and if test is kind of giving you information with respect to this recycle fatigue, then obviously that stress concentration would be also taken into consideration, right? The structural hotspot stress method, which is being used, another way of developing the SN curve is the hotspot stress method, where the welding is done at a particular location, and that causes a stress concentration. It is again, how it is done is that you find out the, I mean, you do a finite element analysis, find out what is the nominal stress at that particular location where the welding has been done, and you apply a multiplying factor. So that is how the structural hotspot stress method is being done. So you have a factor to account for that increase in the nominal stress, and that is being then used to find out the stress range, and then corresponding uh, uh, the fatigue strength is being assessed. So you all might remember from your IS 800 2007 that this is the fatigue curve that you see for normal stresses. There is another curve that is given for the shear stresses that is developed, right? There is no complex loading that is given. It is either normal stress, pure stresses, or the tensile stresses, shear stresses, pure flexural, pure torsion. That is all that this particular curve indicates. And you have shear stress also in terms of that. There is no complex like combined shear and flexure we are not talking about here, like that kind of combined loading is not there. This is SN curve for normal stresses, like a top of a flange, you have normal stresses that is developed when it undergoes bending. So you're looking at such kind of normal stresses, and you have details, structural details that have been given, right? You can see this, what this particular certain diagrams are given here, the table that goes with rolled and extruded products. So you have plates, you have rolled steel I sections that is given there. For such kind of a detailed category, a number is being given, 180. right? So what does this 118 refer to? Each detail category is designated by a number that represents the reference value of the fatigue stress range at 5 million cycles. So if you look closely, the 5 million cycle is here, right? So if I look at 5 million cycles, there are certain numbers that are written here: 133, 118, 103, 92. So you can look at this 118, that is a line that is here at 5 million cycles. The 118 corresponds to this particular dot here, right? If I look at it, 5 million cycles ke corresponding, what is the stress range? That stress range is the same name as the detail category that is being given there, right? Understood? So you have an SN curve where the y-axis is the uncorrected fatigue strength. Uncorrected means, it means some correction needs to be done. What is the correction? We'll come to it. The correction is with respect to thickness of the plate. The correction is with respect to any partial safety factor that needs to be considered. If the specimen or the deck is, or the eye girder is accessible for any kind of repair or this thing, the correction or the partial safety factor that I apply will be very low. If I cannot access it, if I'm not able to look at what is the flaw or the propagation or anything that is there, then the partial safety factor, you understand, it will be very large. So if I take a fatigue strength, uske basis pe I need to change it or correct it based on thickness of the plate as well as the accessibility or things in which how can I can maintain that particular material. Accordingly, the fatigue strength will reduce. So you have a detailed category. So you have an uncorrected fatigue strength, number of cycles on the x-axis, and this particular 5 million cycles is the point at which you see the detailed category has a number which is associated with it. This particular SN curve for normal stresses has two slopes, one with respect to m is equal to 3 and m is equal to 5. Your code gives equations for also these curves. Rather than looking at this table and making a mistake of identifying what is the stress range or the number of cycles, the code gives you formulas to calculate these values also, right? So you have two particular slopes accordingly. And with respect to this particular curve, again, this we have already discussed. The fatigue limit is with respect to our structural steel that we are using, that E350, E250. That kink that happens at 5 million cycles. Like you can see the slope happening, going for the slope of m is equal to 3, and then it changes the slope here. So previous slide I said for ferrous alloys, such a kind of kink is seen where the fatigue limit can be defined. But in certain alloys, non-ferrous alloys and aluminium, there is not, this kink doesn't appear. So fatigue limit is taken like somewhere around 10 power 7 kind of a cycle, it is taken like that. So this is the fatigue limit for where we define that infinite life will be obtained. But remember one thing, there is a definition में एक addition आ गया है constant amplitude के लिए. So earlier we said, like, if I have to get an infinite life, I have to keep the stress range below the fatigue limit range, right? So if I have to keep it below the fatigue limit range, but what type of a loading are we talking about? Are we talking about variable loading? Are we talking about constant amplitude loading? So here you should understand that this particular SN curve, the fatigue limit, which is defined at 5 into 10 power 6 cycles, is for constant amplitude loading, right? And the cutoff limit that is there, FL, corresponds to 10 power 8 cycles. So now comes the full picture, that if my stress range is below this particular point for this detail category, right? I take the last line which corresponds to detail category of 27. For such a detail, you can look at the detail category. There is rolled section के लिए एक है, welding के लिए बहुत सारा detail category बोलता है. So for this 27 detail category, if I keep my stress range below this particular point here, I'm getting infinite life under constant amplitude loading as well as under variable amplitude loading. But if I keep my hand right now at this location, and I say, if I, for detail category 27, if I keep my stress range below this particular line, I have infinite life. I mean, I need not even check the fatigue strength of that particular detail if the stresses are below this particular line for constant amplitude loading. I hope it is clear now, right? For anything beyond that particular level for detailed category, you need to find out what is the fatigue strength. Infinite life nahi hai, it is having a limited life. So you need to cater for what is the demand and what is the capacity of that particular, what is the fatigue strength of that particular detail. right? And code also has a certain provision of saying that when to avoid fatigue strain, that will come to it. Key cup fatigue analysis can be avoided. Cup, it should be included. It is given in the code that is there. But let's look at an example first of all, right, to understand whatever we have covered so far. So a crane girder, a gantry girder, which is similar to a bridge in terms of saying that we want our stresses to be within the elastic range itself. Now you can see a certain trait that I've given here, that the span is 6 meter. The girder section is a rolled steel section, ISMB 400. If you remember ISMB 400 देखेगा तो उसमें जो thickness of web and flange is there, it is less than 25 mm, obviously. So that correction factor for thickness need not be done. The capacity of the crane, this is what you see here. The capacity of the crane is 150 kilonewton. And the gantry girder, let's say this image, there, if the girder is here supporting this particular crane is there, it takes 80% of the total load as a reactive load, which means the crane movement is possible. So it might reach near to one particular gantry girder which is supporting this particular crane. And it's this, we are not talking about this girder, we are talking about a girder which might be like this black line can be a representative of that particular girder at both ends. So if the crane moves towards the left side, if the crane moves towards the left side, 80% of this particular load might come onto this particular gantry girder that we are designing. That is what we are saying, 80% of the total load as a reactive force we have to consider for one particular girder. And then we are talking about कि ये operational कैसे रहेगा. It is assumed that this force is applied as a girder as a single concentrated load. It is the assumption as a designer I am taking, and this gives me an idea about अरे इसका fatigue number of cycles, how much will be there, gets from the operation that I'm going to do on it. So the crane operates for 200 days per year and 8 hours per day and makes 3 trips per hour, right? And the design life of the building is 50 years. So what is the first step that we can take? Okay, what is the number of stress cycle that will come onto this particular girder as it is? So it is 3 cycles per hour, 8 hours per day, 200 days per year it will operate. Since the service life is only 50 years, the number of cycles comes out to be 2.4 into 10 per 5 cycles, right? The next idea, next data that I can gather from this thing is, it is ISMB 400 which is being used as the um, uh, uh, gantry girder, which we are looking at. So it's a rolled steel section, which means from that particular identification I can choose my detail category, which is 118. Understood? So either I can read directly from the table as the 330 MPa, or I can use the equation which is given here, is that the fatigue stack I have to put 118. You remember, it is for the 5 million cycle, the fatigue limit is what is the value that I'm reading for that particular category as 180. A number of cycles I have calculated and I get 324 MPa. This P should have been capital M, capital P and A. 324 MPa is the fatigue strength of that detail. So this is the capacity of that girder when it is subjected to 2.4 into 10 power 5 cycles of loading, and when it is accounted for a rolled steel section, right? So there is no correction for any thickness here, but there is a partial safety factor that comes into picture. Now, if you look at partial safety factor for fatigue, you have two concepts. One is fail safe and one is non-fail safe. So these are two consequences that we are talking about. Fail safe is like we assume that ठीक है क्रैक आने दो फ्रैक्चर में, मतलब fatigue के अंदर let the crack happen, but let it not propagate very soon. I'm okay with a crack appearing in a fatigue, but I don't want it to matlab fail pretty soon when the crack, I mean it can propagate, it has enough life in propagation, means it's a fail safe. But there will be structures where you will have to go for a non fail safe kind of an approach, where I don't want any kind of crack initiation to grow in it. So what do? I have higher factor of safety to be applied onto my as a partial safety factor. So what do? This is the uncorrected fatigue strength or the capacity of the member. I divide it by the partial safety factor there. If I'm going for a fail safe approach, I'll use 1.15. If I use for a non-fail safe, I would go for a 1.35 here. Now, two distinction is, okay, if I can do a periodic inspection, maintenance and accessibility to the detail is good, partial safety factor is less. If the periodic inspection maintenance to the detail is poor, the factor of safety is more. You can understand easily why things are so as it is. And this is how I can directly read from that particular curve as 330 ka value kaise aaya, rather than using this equation here. But it's good if you can use the equations and go ahead, right? We got the capacity, the fatigue strength of that particular gantry girder, we have got it. We have to find out what is the stress range that is generated in that particular gantry girder. So how do we do it? We had an assumption that we had taken is when the crane moves, 80% of load is going to come, and even in that 80% you can consider it as a point load. So I'm finding out the moment that is there, and then the stress m by zk basis may I find out the 0.8 80% is considered here. M by Z I calculate, this is the stress, maximum flexural stress that is generated in that gantry girder. That particular value is in the elastic region itself. So one thing is, okay, gantry girder like bridges should not go into the nonlinear range. So one check is with whether that stress is within the elastic limit or not. We look at it. So 176 is less than the 250 grade of steel that I'm using. So it is okay. And the stress range is 176 minus 0. So in an unloaded case, the most minimum value is 0. And in the loaded range, it is 176 that the peak value can go. In case of bridges, the 0 can go into negative phase also. It can go into positive phase also. So don't take all cases as 0. You apply the rolling loads. You see what is the stress fluctuation that can happen. The stress can fluctuate between 0 and tension. It can fluctuate between tension and tension. It can fluctuate between tension and compression also. So you have F max minus F minimum. Even compression has to be also considered when you look at the large range. It is not plus 40 minus 60. I mean, compression में minus 60 जा रहा है और tension में 40 जा रहा है. The stress range is 100. So 40 plus or 40 minus of 60 will come in. The stress range will be that much. So once we calculated the stress range, it is 176 MPa, and the corrected design fatigue strength is 282 MPa. So with respect to this, we say, okay, this is very fine. So the girder is safe itself. We can find out. The same thing goes for shear force. So we have checked it in flexure that the girder is safe. The fatigue strength is much higher than the stress range that is developed in the girder due to the movement of the crane. And we now check for the shear. The shear ke liye we find out, okay, what is the reaction force that is coming divided by the depth of the girder multiplied by the thickness of the web will give me the shear stress. Here one check is done, 27 divided by 1.15. This is one check that is given, will come in the next slide, which the code says is if your shear stresses are less than a particular value, then there is no need for any strength check or the fatigue strength check for shear. No need to be done. But we have still gone forward, use that formula for that one particular graph that is given for shear check also. We have inputted our detailed category. We have inputted our values for number of cycles, and we have found out what is the value of the fatigue strength in shear for that particular detail. It is 216 MPa. So you can see the very low shear stress is getting developed due to the loads that are applied. So everything is fine. So this is the uncorrected and this is the corrected value. Uncorrected fatigue strength in shear, this is by using that partial safety factor. This is the final value, 188.3 MPa. Again, P should have been capital. It is much higher than what is the demand that is coming in terms of 16.85. So here few things. We have done an example wherein we have checked the flexural strength and the shear strength under fatigue load using the SN curve that is given in code. The same as there in RDSO code. The number of stress cycles will not always be the same. I mean, what you have to keep in mind is certain points that the number of stress cycle will not always be equal to the number of load cycles, which means you are in case of a vehicle moving on top of a bridge, you are not saying that, okay, one wheel has moved in, so there will be only one stress cycle. There are multiple wheels moving behind. So even for that particular rolling motion, there will be multiple, the load cycles will be, many will be there, right? And then dead load is already present in the structure. There is no fluctuation due to dead load that is going to happen. The problem that happens in fatigue is due to the change in stresses produced by the moving live load. So dead load as it is not kind of creating a problem for you. It is the fluctuation of stresses when the live load moves or the vehicle moves. That is where the fatigue analysis comes into picture, right? Now, one small calculation, a reverse calculation was done that if my flexural stresses is 176 MPa, if I do a reverse calculation of for that particular 118 category, How many number of cycles can it, you remember that limited life and infinite life. So what is the limited life that my girder can take up is this many 1.46 million cycles it can take up. Whereas when we did our calculation with respect to the number of hours it will be operational over the year and what is the service life, it is only like 24 into 10 power 4 kind of cycles only it will be subjected. So if I do the calculation also, it is coming safer in that particular value. So that is how we have done the calculation, and here I am explaining what is the difference between the safe life method and the fail safe concept. The safe life method is where emphasis on preventing the crack initiation. Designer estimates the load spectrum. I mean, we don't want any crack to happen any time anywhere in the building. It's a very critical structure that we are designing. Then which structure is component, and components are analyzed to obtain their expected fatigue life. You apply a factor of safety, a higher factor of safety is applied such that safe life method is assumed. You have seen that what it is. And the fail safe concept is even if crack in the main member appears, there will be sufficient strength and stiffness in other members to enable the structure to be used safely. So and but that particular crack जो है वो बनने को तो हम allow कर रहा है, we are allowing the crack to happen. But then what needs to be understood is, yes, you should be visibly able to check whether fail safe concept can work only if you have that confidence that you can identify the crack through NDT methods or through visual observation, such that you can have a control over how much it can take up, like whether the fatigue life assessment is good or not. It depends. I mean, you should be confident enough to do that. Now, with respect to fatigue assessment, I said code gives you when to do fatigue assessment. So it gives you like members supporting lifting appliances or rolling loads, members subjected to repeated stress cycles from vibrating machinery, members subjected to wind-induced oscillations of large number of cycles in life, members subjected to crowd-induced oscillations of very large number of cycles in life. So you have this kind of structures wherein the fatigue assessment has to be done. But if your highest normal shear stress, I mean this calculation normal stress जो है आपका 27 divided mu c by gamma ft, हमने अभी calculation किया था ना 67 वाला. We have checked whether the shear stress has to be, I mean the fatigue assessment has to be done or not, can be assessed based on this particular formula. Mu c is the correction factor for thickness, I said. Gamma mft is the partial safety factor for those fail safe and safe life kind of concept that is there. If your stress range is below this particular level in the normal stress, no need to do any kind of fatigue assessment. If shear stress is kam hai, no need to check for the fatigue strength under shear loading. And if your number of cycles is much less than this particular value, there is no need to check in for fatigue here. Now, in terms of an example with respect to bridges, what I want to show here is we have created a model of a bridge, 63 meter RDSO bridge. We have created a model. In that fatigue assessment ke liye, if you look at the code, whether it is IRC or the RDSO code, fatigue assessment you are not doing for the design loads that are moving on top of it. Maybe RDSO loading, if you apply, there will be trains of loads that you do. In IRC, you will have that 70R loading, Class A loading, Class B loading, which you use to design your bridges, etc. But for fatigue, if you check, there will be a specific set of loads, mandated loads, which needs to be run over the structure to check the fatigue analysis. There is a truck loading, which is given in IRC code. That truck with a certain axle load, axle distance has to be provided or run over the bridge to check the fatigue analysis. Same way for our RDSO, 11 classes of RDSO 25 ton 2000 loading has been provided, which needs to be run over the bridge to check the fatigue life of that particular bridge. So what we have done is we have run the loading, the 11 types of fatigue assessment loading we have run over this particular bridge. It can be run over with different speeds. I think Mohit in today evening class, he'll tell you how to run moving loads over this particular analysis model of bridges, etc. But what is interesting to see here is, we said, okay, there is a cutoff limit for fatigue, which is applicable for both constant amplitude loading as well as for variable amplitude loading. But the fatigue limit at 5 million cycles that is presented here, it is only there for constant amplitude loading. सब तो सही है, but you see that for when the bridge is run over by a vehicle, the loading is not a constant amplitude loading. It is like a variable. It has variations in its loading cycles, right? So what you do is, you run the loads which are designated for fatigue analysis, you find out what is the variation in the load that is coming, and find out what is the stress range that is developed. So if you can identify from the bridge what are the members in which, like let's say you have inclined members that are coming in, where as per truss analysis you get axial load variation in this particular member. But the question comes, out of all the diagonals, which diagonal is more critical, or where the maximum stress range is going to happen? You need to identify that. If you identify it, then you can limit your diagonal member ka fatigue assessment to that particular kind of member, and do your assessment using any finite element software. I mean, you have to go to the nitty gritty, right? You have this member might be two channel section kept back to back with a batten plate on top of it. So welding is going to come, that batten plate stress concentration is going to come. So somewhere FE analysis or something needs to be done to go even into minor detail. But even before going that, if you make a line model of the truss member, do your moving load analysis, you need to identify which is the member in the diagonal which is more critical. So if you do, I mean, if you talk to people who have done bridge monitoring, and they have pasted strain gauges, etc., when the vehicle loading is moving, ask them which is the diagonal member or vertical member, or which is the horizontal member that is subjected to the highest stress range, for which fatigue assessment, if I do it for that, if I'm okay there, I'm okay for rest of the members, right? So in terms of diagonal, I can tell you is that the end diagonals is more critical. But if you have kind of bracings and all, I mean, dimensions is reduced, then the next most diagonal member will be the most critical member that we have seen with respect to the fatigue stress range that is developed. So coming back to our analysis, yes, we say that in case of a bridge analysis where the vehicle is moving on top of the bridge, the loading type might not be a constant amplitude loading. It might be of a variable loading that is on top of it. A variable loading history might is coming on top of the bridge. So what to do now? So for this particular variable amplitude loading, in order to assess the fatigue stress, there is a rule that Palmgren and Miner has come about, which helps you to assess the fatigue life using the curve, SN curve that you have in the code, right? So our code, we said, okay, 5 into 10 power 6 is for constant amplitude loading. It is not consideration of with respect to variable amplitude loading. But yes, beyond 5 into 10 power 6 and below 10 power 8, there is a range where variable stress can create certain problem for the material under which the fatigue is being assessed. So Palmgren Miner came up with this particular rule for variable amplitude loading, of assessing the fatigue strength under variable amplitude loading. And his linear damage rule, जो है linear assessment जो उसने किया है, has two assumptions that is being considered. The first assumption is damage fraction resulting from a particular stress range level is a linear function of the number of cycles in that particular stress levels. We'll do a small, I mean, I'll show you what he means by that. I mean, he's saying that, okay, the damage that is accumulated in a particular stress range is proportional to the number of cycles that the member or the assembly is subjected to in that particular stress range. So that is independent कि एक damage जो हुआ जिस stress range में हुआ उसमें कितना number of cycles है वो proportional है. And the second thing is total damage of all stresses. The total damage of all stress range levels in this is the sum of the individual cycles. So now once we have identified, okay, there is a variable stress range, variable loading or the variable stress range that is there, we identify a particular stress range, usme kitna number of cycles are there, and under that stress range how many cycles that the assembly can cater for. And then we accumulate all of those stress ranges and look at our SN curve to find out what is the final life of this particular thing. So think of it. I mean, if the way in which I spoke is not clear, let's look at this variable amplitude loading, right? I look at this variable amplitude loading and I find out that there are certain stress ranges which are repeating. I group them together. So I have a stress range F1 which is being repeated 3 times. N1 represents the number of cycles that is there. F1 represents the stress range. So I have 3 groups of stress ranges occurring over N1, N2, N3 cycles independently. So I have to break down this particular stress range cycles. I have to break it down into based on the stress range, and I have to identify how many numbers of cycles that it is undergoing, right? This is an analysis results. So what I look at is okay, I look at my SN curve. I have my SN curve here. I look at what is the stress range that it has undergone. So F1 ke liye, what is the number of cycles that section can undergo before fatigue failure, right? I'm looking at that SN curve of my code. I look at what is the stress range that is developed here F1. I look out what is my total value of cycles that member can undergo. So I have two ends here. One is N1 related to what is actually the member undergoing due to a particular loading, and what is the value of N1, capital N1, with which that particular assembly under that stress range can survive. That is a fatigue strength of that particular. I divide small ni by capital Ni. Right now, I have another fatigue range or a stress range that is coming. I have F2 K. For F2, I'll find out what is a capital N2. I already have from my analysis, let's say MIDAS analysis or SAP analysis, I got what is the number of cycles that is undergoing. N2 divided by capital N2. Same I do for small n3 divided by capital N4. I sum it up. That is Ni divided by capital Ni ka summation if I do, and I have to keep it below the range. And this range normally in the code is taken as 1. If I keep it below 1 for the variable amplitude kind of a thing, I can ensure that my fatigue strength, it will be safe in fatigue. That is how the palm green minor rule applies. I hope it is clear, right? So I break the variable amplitude loading into independent stress ranges. I count the number of cycles that has occurred due to the moving load analysis that I've done using MIDAS or any other software. And then I look at key from my SN curve for that stress range, what is the number of cycles that it can survive without any fatigue damage? That is a capital N. I find out those ratios. I keep that ratio or the combination of this ratio below a certain value of 1, let's say. But experiments have proven that the value can be from 0.7 to 2.2. Right? Why this variation? Suddenly, when I said 1, it seems makes sense. But when I look at experimental results, it is like from 0.7 to 2.2. So even this linear damage rule that palm green miner has come about has certain flaw in it. What is that flaw in it? I mean, this is the same thing that we have explained. What is the flaw is that one thing is he doesn't assume the sequence of loading. So if there is a stress range of 10 that comes up followed by a small stress range of 5, 5 MPa, like 10 MPa comes first, 5 MPa ka stress range comes later. His rule doesn't come ki who has come first and who has come later. So the 10 MPa cycle might have produced a larger slip in the material. 5 MPa might have done a lesser slip. So the sequence of loading he doesn't take care. And the second thing that he doesn't do is damage accumulation, which means the same thing that I said. 10 power 5 के ऊपर 10 power 5 million cycles के आगे, if my stress range is below that 10 power 5 cycle का fatigue limit for a particular detail category, the minor rule doesn't look at what is the damage getting accumulated due to variable load. I said a constant amplitude loading ka detail will have an infinite life beyond that fatigue limit if the stress range is kept below the line for that particular detail. But for variable loading, that damage which is getting accumulated is currently ignored by the linear palm green minor rule. So the shortcomings are there. That is why this particular, see, linear analysis is easy to do. Non-linearity brings in more problems. So most of us do linear analysis in terms of our bridge or any kind of assessment. But yes, if it is a mind critical structure, non-linear analysis needs to be done. And for that, non-linear damage rules are also there. Right? Non-linear palm green minor rule. I mean, the kind of non-linear versions are also to be done. But most of the cases, this is like variable loading. I mean, जो हम bridge के लिए करता है, linear is good enough for our assessment. Now, if my loading is variable, then it's easy to say by looking at this curve, यहाँ तो सारा clear है कि भाई I can find out the stress ranges easily. I can group them up, but life is not easy as it is. So there should be some kind of numerical methods. And the stress cycle here, there were only 3 ranges. Totally 9 cycles were shown in that particular curve. If a vehicle is moving, there will be a number of stress ranges that is going to come up, and the variation will be very high between the stress ranges that is going to come. There will be variations like in terms of the tension, compression. The cycles might go from one range to the other range. So in terms of that, it will be difficult for us to count these stress ranges to do that SN curve wala thing. So if you look at this thing, the variable amplitude has somehow been brought down to a constant amplitude kind of a loading, and then only the progression has been done. So how to bring a variable amplitude of a very large nature into case of a constant amplitude loading? The reservoir counting methods like reservoir counting, rainflow counting, peak counting, simple range counting methods are there, where you need to do a MATLAB coding or a kind of such kind of things needs to be done, such that your life becomes easier to do this kind of counting. So let's say we have a variable amplitude loading like this. It is highly variable. It's not looking as simple as the one that is earlier was there. How does the rainflow counting method is there? We go from hill to the bottom of the hill, and in this diagram we move from the bottom of the this thing to the top of the hill. So what first we'll do, rainflow may let the rain flow from top to bottom. So I say from point A, the stress range jo mila hai, that is 70 MPa, let's say the rain flows down. The value at point C corresponding to C is less, so the rain continues, the water continues to flow. The peak value, I'm looking at only hill and this particular diagram, rainflow from tension peak is what we are looking at. This value is lower than 70, so the rain continues. Again, this peak is lesser, so the rain continues. It follows this boundary. This is low, this is low, this is low, so it continues till it reaches this particular point, last point. So the first point is the highest stress range, so I have a rain which is flowing like this. From point number C, I again make my flow. But yes, the first flow, I mean, I'm telling you how the method is. It sounds kind of silly in terms of telling you all this, but understand the thing is, it's just counting the stress range that is happening. I mean, how will I identify constant amplitude from a variable amplitude is what I'm doing here. So from 2 it goes down, from this particular 30 MPa it flows down because of this particular rules that I mentioned here, which you can look into textbook. It is restrained till here because there is no peak that is, this particular peak is here, but even the higher peak is here, so it gets restricted here. Then I take the second peak, I bring it down, I stop it here because this particular level is higher. I bring this one down because of this rainflow, it stops here. This peak is stopping here because there is another peak that happens beyond this particular value, and this goes down and gets stopped by this particular flow which is already there. And then this peak is happening, it stops here, right? Same happens if I do opposite. I start from the bottom portion, from the compression peak to the highest value. I do this. See, I am stopping this rain flow here because the next peak of compression is higher than this value. If this was lower, I would have taken the flow as I had done here for a longer range. So this stops till here. This again goes till here because this range is lower than this. This goes till here. This goes till here. And I do the same exercise for the entire range of loading that I have. Then what I do is I pick one from the tension cycle. If I have a matching value from the other compression cycle, I match it and group it together. I mean, as simple as that. From you can see the numbers here, 1 to 6 dash. You can read the textbook, or you can after you get the slides, you can see why 3 and 3 dash have been grouped together is because their stress range matches. 70 to minus 90 वो जा रहा है, similar stress ranges का जो flow है उसको हम group करता है. So we get equal from variable amplitude, we get the constant amplitude. And what do we do next? We look at what is the stress range for these particular things. So 30 minus 20, which is 50 MPa stress range. How many of such number of cycles are there? We count them. Once we have got the stress range and the number of cycles that is there, we again go to Palmgren minor rule and see what is n by n, summation of n by n. If it's less than that value, it works for us. So the same thing has been done for this particular bridge model. We have looked at we have used MATLAB to do the rainflow counting. So we have number of cycles of stress range 2.5 MPa. We have number of cycles are more, uh, and higher amplitude is also there of stress range, but half cycle or a one cycle is only there. We use the Palmgren minor rule and we say, okay, my particular detail of, let's say, an inclined member or a flexural member, number of cycles that it can take up is this particular number of cycles. Now if I have the data from the running time of train or anything like that, how many times will a train of a certain load will pass over that particular thing, I can do my analysis and see whether my number of cycles that the detail can carry is less than the or more than the demand that is coming, then everything is safe for me. Now, certain discussion points is like, okay, normal and shear stress, exclude the stress concentration due to geometry detail. You need to consider that. Normal and shear stresses should be determined considering all direction design action on members. So what these points are giving certain things that, okay, even if things have been simple on your ears right now, there are certain things that you need to consider XYZ with respect to the detail that you're looking at, the loading that is going to come up, and the stress analysis जो आप कर रहे हैं, section sizes क्या है, slenderness ratio क्या है, that needs to be considered. Now we said, okay, we are looking at only normal stresses and shear stresses. What if combined stresses come in? What if combined normal and shear stress act simultaneously on the member? I mean, significant. I'm talking about significant. I mean, insignificant के case में जैसे for that gantry cut, the shear stresses was very minimal. The normal stresses was very high. So in those cases, yes, it's value. But sometimes it value, if it increases, what you need to do is instead of normal and shear stress ranges, principal stress should be calculated and stress range corresponding to principal stress should be used for fatigue evaluation. As simple as that. You then look at fatigue strength in terms of the principal stresses that are developed. Now the question comes. Now the important discussions that needs to be considered or thought about here is, whatever we are designing as a structure, whatever bridge girder जो हम design करके रख रहा है, that is for the pristine condition of steel, and also thinking that some kind of maintenance will be done over the steel girder that is being done. What if corrosion happens? So people, what they have done is they have taken steel fiber, steel rod, steel plates also they have done, and they have done aggressive corrosion, or what do you say, accelerated corrosion test, like maybe immersion test specified in ASTM, whether that is salt spray chamber test or things like that they have done. And they have done the SN, they have developed the SN curve for that particular kind of thing. And you can see that if my corrosion ratio increases, if my corrosion percentage increases in my member, for the same size of detail, my fatigue life reduces. If the corrosion is less, then my fatigue life is higher. So corrosion does play in terms of the fatigue strength of your steel, right? Does our code take into consideration any corrosion? If you read your clause in your code that is given, it says it is for mild corrosion. These curves or these details or this SN curve that is being given is for moderate, mild to moderate kind of corrosion is being covered. What about severe corrosion which happens near the sea? Or what if severe corrosion does happen if you don't maintain that particular thing? So it is a very critical thing that needs to be considered by all of us, or those who are designing the structure and those who are doing some research work. You need to consider. So look what is happening to the corroded steel. Yes, you can ask a question, accelerated corrosion is not a real corrosion. Yes, it is true, truly enough, but then some factor of safety, I mean, correlation between real corrosion in the atmosphere and the accelerated corrosion which we are doing in some chamber or immersing in some salt is not really equal. There are no relations right now to kind of predict. It may be true for one city, it might not be true for another city, what you are doing trying to do between atmospheric and accelerated corrosion. So you can see a person has done a coupled corrosion here, which means he has not corroded the steel plate separately and then done a fatigue test. He is doing the corrosion simultaneously with the fatigue and try to develop a curve alongside with it. So what do you see? You see the stress strain curve of the material that is there, and you can see that if the material is not corroded, it's a pristine steel, it has a good yield strength and it has a good ductility. Percentage elongation is high. But if you corrode it for 10 days, irrespective, don't think right now whether it is really mimicking the behavior or not. Think what corrosion is doing. That if corrosion happens, the strength has reduced and the ductility has reduced. If you corrode it for 40 days, then the ductility and strength has totally reduced. So how are you kind of, and one more thing, I mean, percentage ductility and yield strength are totally decreasing. So earlier, the conception was if corrosion happens, the thickness in the member is getting reduced due to the corrosion activity. But then you are having an example here which shows that yield and ultimate strength and ductility can also reduce. So which means which changes the whole thing. I mean, if you design a bridge for a higher strength of steel, higher strength, if you design a bridge for a particular steel grade and it undergoes corrosion, it is not being maintained properly, then your stress range is also going to increase because of your thickness loss of your member. but your original capacity, maybe you wanted the stress range to be within the yield value, yield strength of the material, but suddenly if you're getting such high reduction, it might even go into the non-linear range, right? So there is a high risk there, right? And correspondingly, if you prepare an SN curve, you observe that if the pristine steel has a certain SN curve, the corroded steel has a different SN curve totally with respect to what is being done. Now what I said earlier, like if I have a grade of steel, you might say someday say, sir, today in the market E450 grade is also available, shouldn't I make my steel truss bridge using E450? In justification for your demand, you will say, sir, if I use E450, my member size will reduce and that will give me economy in my construction. And you yourself said with respect to this particular calculation that the fatigue strength, the fatigue limit jo hai, that is proportional to the ultimate strength in the steel. So if my ultimate strength of steel increases, my proportion fatigue limit is also going to increase. So won't it work in my favor? So in that, some researchers have done, I mean, in terms of, you can really see S690 is a higher strength grade steel. You can see from the stress strain curve that S690 ka yield strength is very very high, around 750 MPa, whereas S355 is kind of a mild steel where 400 MPa is the yield strength of that particular steel. If you look at these two curves up and below, this you can understand that elastic strain amplitude and number of reversals to failure, which means this is kind of a high cycle fatigue where the stresses have been kept below the yield limit. And here is plastic strain amplitude, means this is a low cycle fatigue where I have pushed the material into the non-linearity, I have applied the cyclic loads, and I have assessed the low cycle fatigue capacity of that particular material, which is both these grades I have assessed. You look at where the graph is lying, the SN curve for the high strength steel is lying above the low strength steel, which means right now you are happy in stating that, okay sir, that confusion was also removed, that if I use a high strength steel in my bridges, I need to only take care of, it becomes a lightweight bridge, which means the fluctuation of stresses will be higher than what earlier was. The stress range is going to increase. If I cater my section size with respect to that, then I'm getting a higher fatigue life if I go for a high strength steel. But if you look for a low cycle fatigue test mein, you see that the curve for the high strength steel is below that particular curve. So suddenly you're not getting as much advantage, which means if I say in terms of the application of high strength steel in earthquake case, you have a problem at your hand, which means my fatigue life of a high strength steel under low cycle fatigue, where the deformation might go into the non-linear range, is very less. So here is a what do you say, conflict of idea, that if you have a high strength steel, go for in bridges also, but many other things also will come into picture. Stress range will come into picture. Lightweight section undergoes higher amplification of dynamic amplification, so comfort of the passenger, rest everything will come. I mean, your material cost will reduce because you get a slender, or a, well, slender is a bad word, lighter bridge section. But if you look at the earthquake, you will say, okay sir, in a high rise building in a high seismic region, I can use a high strength steel, but you need to be careful, you need to assess this particular thing. I mean, it's not bad, I mean, having a curve below the stress range is not bad. Comparatively, high strength steel is performing bad in low cycle fatigue. You have to check what is the stress range that you're getting from your analysis, and then finally say whether it is applicable or not. The only thing that I've done here is there is a variation in the SN curve for high cycle high strength steel and a low strength steel kind of a material. Also, another thing that was observed, that in high strength steel, the propagation, let's say crack initiates, the propagation of steel is very quick, which means if you go for that uh, uh, not the sorry, fail safe wala condition ab jayega, jo which I had explained earlier, high strength steel is not the appropriate material, which means you wanted, if a crack is already there, the propagation should be also in a very stable manner, not in a very quick manner, in which S690, the high strength steel, was showing a very quick propagation of the fracture also. So these things have to be considered while you do the fatigue analysis, right? So with that, I hope it was a fruitful kind of a discussion in terms of the fatigue assessment, which we have kept exactly um, this thing, what has happened. So you need to look at in terms of fatigue analysis for bridges. as well as buildings in different manner, different concept. For high strength steel and low strength steel ke case mein, you have to think little bit deep. It's not very complicated, right? Steel structures are not very complicated. Accordingly, you will be safe if you do it properly. Even welding, if you do properly, there is, I didn't say anything against welding today. If you do the thing properly with the proper procedure, WPS, welding procedure scheme, is always there for a fabricator to do the process. Normally what happens at site is nobody follows it, so you end up, you do only DPT test. Mostly, most of you must have seen that. Nobody does a UT or an RT test to check whether there are flaws in the member or not. This needs to be done rigorously so that you avoid such kind of failures. Yeah, man.
Thank you, Ashwin sir. Can we take up the question now?
Yeah, please.
Okay, Mr. Milind is asking whether box type bridge is checked for fatigue load or not.
No, any steel bridges, any bridge needs to be checked for fatigue loading. It comes, and I mean, bridge ke case mein it comes fatigue, as I said. For a steel bridge in any case, uh, more than the strength and this thing. See, it is not about being a box. It is about, there are bolts in your box sections, there are belts in your box section, there are plates in your box section, there might be stiffeners in your box section that might be subjected to a certain level of stresses. So according to the details that you have, I mean, I said na, there are different details. We looked at only 118 detail category, which is a rolled steel section or a plate. There are further details that are given in the fatigue curve or the code that is there. If you don't find your particular fatigue, you need to check with respect to key. If you don't have that particular detail, you need to look at international code, or you need to develop a curve for that fatigue thing so that you can do your analysis. So it is irrespective of the bridge type. It is about the detail that you have given. I mean, if you look at that code, you have details in welding also given in very detail. Uh, uh, Whether it is what you say, fillet welding or groove welding, I mean, different types of details are given. Yeah, man.
Dhruva Jyoti is asking why is the load intensity for fatigue load model generally less than normal live load model?
No, it is like normal live load आपका design में. I mean, I didn't show anything like that, and I don't want to comment whether the fatigue load intensity is going to be always less than that. There is a particular uh, load which is specified to do fatigue analysis. If whatever that comes in, I mean, you are already using a certain load to design your structure, being done for a certain speed or etc. Fatigue analysis may, you need to check I mean, the code says this particular load needs to be done. So there must be some kind of study that must be done, which governs like, okay, this load is more than enough as a representative load, that this is more than enough to do the fatigue analysis. So whether that comes below your normal analysis or not, that is okay, but because you are designing the structure for the live load that is there for a static condition, with yes, some dynamic augmentation factor is also coming into picture. But for fatigue, which undergoes this fluctuation, and the SN curve that features comes in, some kind of a correlation will be there for that load and that fatigue limit that you're calculating. So that is why the code says independently do the analysis for fatigue using this particular load.
Okay, Mr. Sayyar is asking, in context of slide 38, 39, and 40, please put some light on the suitability of methods in different applications and in context of fatigue design methods. That is
Okay.
infinite life design, safe life design, fail-safe design. Are the design provisions same for all methods?
No, maybe we can reply it in detail with respect to these slides. I hope you have the yesterday's questions also there. I'll
Right,
prepare a
I
reply
have.
to all of
Yeah.
this, and then individually I can give them a reply.
Okay. Mr. Jay is asking, we are generally doing fatigue check for steel structures. Eurocode specifies to check for fatigue in concrete in comparison and shear and tension in steel reinforcement. For concrete bridge, when will fatigue be critical?
No, see, Jay, in terms of the question that you're asking, I didn't say we are doing only for steel. We should only do for steel. The concept is, you think in clear, in manner that if there is a concrete bridge which has been made very slender, or a lightweight kind of a construction has been done in terms of a concrete bridge, you do a moving analysis. Even there is a fatigue loading, trucker loading. If you remember, if you guys have gone through the IRC code, you say class A, class 70R, class A, all those loadings are there. There is a typical loading that is given for truck kind of a thing. Does it say that do it only for steel or do it only for concrete? It says for fatigue analysis, use this particular loading to do your moving load analysis. So if your concrete bridge, now coming back to your concrete bridge, if it is a kind of, I mean, slabs के case में, if you normal building में we use thick 125 mm slabs, but you have certain hollow slabs being created for doing, getting away with making it lightweight and getting easy on your pocket. So if you have an RC bridge which is light in weight, where cyclic stresses are being, are getting generated, then even fatigue analysis needs to be done there also. Yes, in our code, the structural detail that you look at are mostly predominantly steel, because your self weight of your concrete structures that you normally design are very heavy. So the fluctuation of stresses that we see in terms of fatigue analysis, yes, is governed by, if you look at the detail, it's mostly steel only. So you asking that question is not a problem. But I say, irrespective of that, there might be some stiffness, there might be some anchors in your concrete bridge also, which might need to have a analysis check for fatigue. So don't avoid it. Yeah.
Then there is a question from your previous yesterday's presentation itself. Why we call the time period and natural frequency of first mode as fundamental time period?
Because if you see for yesterday, when we arranged the frequency in increasing order, omega 1, omega 2, omega 3, we got for omega 1 mass participation of 90%, right? So the mode or the frequency which corresponds to the highest mass attribute, or what you say, contribution, that is what we call as the first fundamental mode, because it contributes the maximum amount of mass participation. So that is why I had written that particular thing. Rest are all are natural frequencies of the system. If you vibrate that system on a shake table at that particular frequency, whether it's omega 1, 2, or 3, it will act in a very vigorous manner. But we call the omega 1, and we keep, when we solve that characteristic equation, we get three solutions. Three solutions for a 3 degree of freedom system. We keep it in increasing order, and we call the lowest frequency as the first fundamental, because if you check the mass participation, you will get accordingly itself as the first fundamental one.
We'll
Yeah.
take the last one now.
Yeah.
Mr. Jay is asking, what are the verification tools performed for fatigue where dynamic moving load analysis for high speed is required?
No, validation in a sense that you can do, if at a laboratory level, you can do fatigue testing at a coupon level, at a small beam level, at a girder level if you have a bigger facility. But other than that, it is better that if you have access, if you have permission to a bridge, it is better to attach strain gauges, it is better to attach deflection sensors, etc., and try to assess if you have that design, if you have the basic material property at your hand. It is a difficult, as long as I'm adding numbers there, that you need the material property of the pristine structure, you need to have its maintenance record, you need to have what are the corrosion or anything has happened or not. Once you get the final detail at that particular stage, you need the vehicular data also to come into picture to assess the real data that is there if you do for a numerical analysis. Otherwise, you're just sticking a strain gauge, and you need to have control over the load that is moving on top of it. You cannot say, acha, particular train is going every day, I'll use that data, but you need to have the load also. So I think SCRC ka ek paper hai, long back it was done, where RDSO and SCRC Chennai did a study on a bridge in India, where a vehicle of known load was passed over the bridge, and the assessment of the cyclic stress amplitude was done. It is available on the internet. It is like a good reference. But yes, improvement can be done in the way data acquisition was done in that particular paper. But it is as good as getting a data on the actual thing. Otherwise, I would recommend Mohit to kind of say how the moving load analysis is being done. But yes, validation for such a huge structures are very difficult. You have to look at papers and publications if anything has been done. It needs collaboration between academics, everyone. In terms of RDSO, and everyone has to be done so that validation results can be produced. It's a difficult task. Yeah. Yeah.
Okay, sir. We'll stop here then. because this
Okay.
will join at 2 also. So we'll stop here for lunch break, and at 2 we'll join for Vaisinger's lecture on bearings and base isometry.
Okay.
Thank you very much, Ashwin.
Thank you, everyone.